In programming, in computer science more generally, computer scientists have some shorthand notation for describing how long it takes to run certain algorithms or certain programs. And this notation here just denotes what we'll call big O. And this is it stands for order, the order of magnitude of running time, essentially. So if we have an algorithm like your grade school counting, 1, 2, 3, 4, we do say that's linear. But if you want to be really fancy, you can say that that algorithm of counting is in big O of n. So big O of n is, again, just sort of the mathy way of saying that algorithm, in the worst case, is going to take you n steps, no matter what. Because you have to count every person. By contrast, if we did the twosies counting everyone in pairs, 2, 4, 6, 8, and so forth, we could actually whittle that down to something like big O of n over 2. Right? If n is the total number of people, divide by 2. And though if we went even smarter and had you guys count yourselves, pairing off again and again so that the problem goes from this size to this size to this size to this size, that we could express as big O of log base 2 of n. And realize that this is pretty much as mathy as a class like this tends to get, but you'll find it helpful in thinking through some of your own programs longer term in the future weeks, just as to how well designed something might be. And we'll see some alternatives to this big O notation. In fact, what we're going to see too before long is that an algorithm that's big O of n versus an algorithm that's big O of n over 2, most people just say, ugh, any constant number like that is actually pretty meaningless. Because you know what? If your algorithm is twice as fast as mine, whereby you count in twosies and I count one at a time, well, you know what? All I have to do to catch up to you is wait literally 12 months. I get a brand new computer that's probably going to be twice as fast thanks to industry trends. And voila, now our algorithms are the same. But that's not what we mean by comparing algorithms. So we do, in fact, when talking about how well designed something is, we just cross out things like divide by 2 or multiply by 2, any of these constant factors, because again, it then ties us too much to current hardware capabilities. And so we try to focus only on the formulaic part, the variables. So let's try to make this a little more real. So dramatic flourish time. So in advance, we prepared these white pieces of paper here. Hopefully you didn't see what's behind them, on this blackboard here. And the question at hand is, how can we find numbers behind these doors efficiently, as quickly as possible? And what's nice about this point in the semester is that now, even though you might still be fighting with some new C syntax and functions and return variables and stuff that might be new to you, we at least have a pretty good toolkit for storing information. You've got variables and floats and chars and strings, but we also now have what data structure that we introduced a couple days ago. Yeah, so we have arrays. And an array in English, anyone, is what? How about one person? In words you might use to explain it to your roommate.
It's a collection of data points. So a collection of integers or a collection of characters.
OK, collection of data points, collection of integers or chars or whatnot. And be a little more precise. What about that collection?
There's a finite number of them.
Finite number of them. And can you be even more specific with regard to how they're laid out in memory?
They each take up the same amount of space in a specific order.
Perfect. They each take up the same amount of space, int, or char, 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 and they're all contiguous in memory. And the advantage of the contiguousness of these values is that you can use that very succinct square bracket notation to go from the 0th element to element 1, element 2, element n minus 1. But we did see some dangers. If you accidentally take an array that's of size n and go to the name of the array bracket n, what did you just do that's bad? Sorry? You fell off the end of the array. And now sometimes this might have no bad effect, right? I printed something out where I went a little too far and all we saw was a space character, not a big deal. But if you go a little too far, you're actually going to start touching RAM that does not belong to you. In fact, it might belong to some other program potentially altogether. And so the operating system will typically crash in some form. And the bad news you get from your command line is core dump or segmentation fault, one or both of those realities. But let's assume for now that we at least have arrays. And so we have this capacity to store, say, 8 integers back to back to back. So this might be our first array here. This might be a second array here. And behind each of the doors of paper here on the top, we have some random number in random order. And suppose if I were to ask you to, say, find me the number 7, what would you do in that top array of integers? This is not even a computer science question. I say, here's 8 pieces of paper. There's 8 numbers behind them. It's sort of game show-like. Find me the number 7. What would you do as a reasonable person? Oh, sorry? All right, so rip off the paper, right, and just start looking for it, right? And unfortunately, all of these doors are closed. All of the paper's hiding it. So you can't kind of do this human thing and just kind of skim it and be like, oh, bam, it's right there. Rather, you have to be much more methodical and actually open the door or lift the paper, then let it go, and then check another one, check another one. And this kind of hammers home the point, perhaps, that a computer, too, has to do that. We've had the luxury for some 18, 20, 30 years as humans growing up of just kind of being able to glance at something and say, it's right there. That number is right there. Or looking out in this room and saying, feels like 60 people. And you get this aggregate sense. But what your brain, maybe is actually doing, and what a computer certainly would need to do, is you can't just kind of glance out and say, 60. You have to do something much more methodical. 1, 2, 3, 4, 5. Same thing in Scratch. You might have felt yourself frustrated at first because Scratch kind of confines you to using only specific puzzle pieces that exist. And you kind of have to figure out how to express something like that would be very natural to say, like move the cat up to the left. Well, how do you actually move that cat? How do you move Scratch up to the left? Well, you had to do something like in a loop, and you had to have him move and then turn and move and turn. In other words, you had to break down common sense and human assumptions into something much more precise. So one of my favorite CS50 moments was a couple of years ago when we did a demonstration much like this with one of your predecessors named Sean. Rather than have someone new come up this year, I thought I would engage us in a look back at how Sean approached this problem. And hopefully, as you watch Sean participate in this example here, you yourself will be thinking about what you would be doing or would not be doing if you had been Sean standing in front of some 300 people trying a little example like this. So this is Sean trying to find us the number 7. And again, ask yourself as we watch this what you might have been doing or yelling at Sean at the time. OK, so your task here, Sean, is the following. I have hidden behind these doors the number 7. But tucked away in some of these doors as well are other non-negative numbers. And your goal is to think of this top row of numbers as just an array, or just a sequence of pieces of paper with numbers behind them. And your goal is only using the top array here, find me the number 7. And we are then going to critique how you go about doing it. All right. Find us the number 7, please. No. 5, 19, 13. It's not a trick question. 1. At this point, your score is not very good, so you might as well keep going. 3. Go on. Frankly, I can't help but wonder what you're even thinking about. Only the top row. So you got 3 left. So find me 7. $17. So we never again have to do that demonstration because Sean kind of captured the potential of it so perfectly. So there really was no right answer to that question, right? The best he could have done was just start tearing the pieces of paper from left to right and find the number 7. And I'm sure he was thinking there's got to be some trick to this, and it probably didn't help that all these eyes were bearing down on him. But the problem is that if you're not given any sort of assumptions to go on, you're just told, here's a bunch of numbers, they happen to be non-negative, but they're in some random order, find me something, the best you can do is to implement an algorithm in what running time? Big O of what, if there's n total doors to look behind? It's big O of n, right? So that algorithm, in the worst case, was going to take Sean big O of n steps. And it almost did. It was big O of, in his case, n minus 1. But as we do with divide by 2, even doing plus this, minus this, who cares? We typically erase that part of the formula, and we just say Sean's implementation was big O of n. But there's another way we can express running time. Because Sean could have gotten lucky, right? If 2 years ago he had actually done something slightly different, he might have avoided that whole awkward moment for himself on stage. What could he have done differently, just by chance, that would have made that problem go away much faster? Right, so start on the other end, right? Now, there's no way he would have known that, and had he done that, we wouldn't be showing the video because it wouldn't be nearly as much fun to watch, but he would have solved that problem in just one step, right? So in one step, you would say is the best case solution for that algorithm. The process is the same. Even if he started from the right, most likely he would have just played the same game, but from right to left instead of left to right. So in the worst case, 7 could have been here. And if Sean just so happened to start over there, well, it's the same kind of bad luck. He would be a big O of n. But in the case of good luck, where 7 is here and he starts here, or 7 is here and he starts here, we would say that that algorithm is, yes, in big O of n, because big O is, again, worst case. But we can also express it as omega. Omega of some constant number. And how many steps in the best case might it take Sean to find the number 7? 1. So we would say in omega of 1. So big O parentheses n for the worst case, and then omega parentheses 1 for the best case. And maybe it could take him 2 steps, right? Maybe it actually takes 2 steps conceptually. You have to lift the paper, look at number, and that's 2 steps. But the takeaway is that it's a constant number of steps. Irrespective of how many doors there are, in the best case, the solution to that problem might only involve just 1 step. So could he have done better with these doors? Would you have done anything differently given the same input that he was? OK, so you could try the twosies approach, right? You could at least have kind of made that awkwardness go away twice as fast by checking these 2, and then these 2, and then these 2, and it would take 4 steps maximally instead of 8. So in formulaic terms, it's still kind of big O of n, because it's big O of n over 2, but we said, whatever, with the constant numbers, it's still big O of n. But in reality, that would absolutely have been faster. It would have been twice as fast. If he actually had some way of kind of lifting 2 pages with one hand and then 2 in the other, he could actually do n over 4 and get that over right quick in just 2 huge steps, or lift all the papers at once. But again, these aren't fundamental improvements, and he's really given no additional information he can leverage. If he's told they're all in random order, I mean, sure, you can start in random order. Start here, no. Start here, no. Start here, no. But at the end, you're going to have to check them all. And in fact, if you try this random approach, what might you also have to do if you're now the human or a computer implementing that kind of randomness? You have to remember where you've been. So here we see the first example of a trade-off. Well, you can maybe get lucky and find the number 7 faster, but it's going to cost you something. You're going to need to keep around some variables or another array just to remember what doors you've been at. For instance, you could have another array of size 8, and just much like you would on a piece of paper, you could check off which doors you've been to, that you've opened, but that's going to take you another 8 booleans, some number of bits or bytes of memory. So what would Sean have benefited from? Besides my just flat out saying the number 7's behind that door, what could I have done to at least help him make his algorithm better? OK, yeah, so what if I arranged it in ascending or descending order, right? What if I steal a very reasonable idea that Verizon's been doing for 1,000 years and its predecessors? Our phone numbers are not in random order in this book, and for good reason. They're alphabetical, right? But if they're alphabetical, that's not just convenient. That is an assumption we can now exploit to implement this technique known as divide and conquer. So let's go ahead and